And then, okay, so let's begin our lecture for today. So I'm going to go through what we had for last class, what I discussed at the end of last class. And the overarching theme in the next few lectures is to look at spontaneity, the criteria that we have for spontaneous processes. Okay, and spontaneity is essentially irreversibility. Okay, so how do we sort of, what criteria are there for us to rely upon when we're analyzing the system to say, okay, well, this system is not stable and it will spontaneously or irreversibly evolve to an equilibrium state that is not the current state. And so we want some criteria and some guidelines for that, and a formalism for that. And so this is what this whole section on spontaneous processes and irreversibility is. And then that will also give us some indication about stability. When is a system stable? Okay, so these are the two things that we're interested in. And we've already seen one sort of criterion for irreversibility for an isolated system, and that is the entropy. So there's this thermodynamic potential called entropy, a state function, and we know that in an isolated system, if the system is initially unstable, the system will evolve spontaneously, i.e. irreversibly, to an equilibrium state, which drives entropy towards a maximum. Okay, so that was one of these criteria for spontaneous processes or spontaneity. Okay, so we've seen what that is and we have a flavor for that. So now we're going to codify it by combining the first and second laws through this fundamental equation that I introduced a couple of lectures ago. And we're going to get a very robust formalism for discussing things. So let's begin. So in order to do that, let's go back to our first law and second law. And we saw that the fundamental equation or fundamental relation, if you want to call it, there's several, but this is the first. And it's fundamental because it's composition of two laws of thermodynamics, the first and second law. And we saw that du, which is equal to dq plus dw. This is a general statement of the first law in differential form. Okay, there's nothing here that says we're dealing with reversible, irreversible, what have you. It's just very general. Okay, so we can isolate dq, and this is the way I'm going to do it. So it's not the fundamental equation yet because I haven't said anything about dq yet. But so we can isolate dq. So dq is just du minus dw, which is then du, and dw is minus p external. So the minus minus gives us p plus p external times dv, and that's dq, and that's a very general form. I can let this external be the surroundings, okay? So it's the same thing. If you remember the piston cylinder examples we used early on, all we had was a block or a weight or some external mechanism to induce pressure on the system. That was what p external is. And so we can let that be P surroundings. I want to just let that be P surroundings times dV. Okay, so we'll hold on to this expression. This should not be anything surprising to you at this point. Okay, so now I want to move towards the fundamental equation by incorporating the second law. And we saw that the second law holds that there's this thing called entropy, and that's dq reversible over T surroundings. And we can use T surroundings or T system, okay, T surroundings, because when we looked at the Carnot cycle, we saw that for entropy, when we had a reversible process, right, so this is reversible, T surroundings equals T system, okay, and we saw this in our Carnot cycle right here. So whenever we had Q coming into our engine, so this was the cycle representing the engine, whenever we had heat into the system or the engine, it was at this temperature that was constant. Okay, that's the isotherm, and it was related to the temperature of that heat reservoir. Okay, and that heat reservoir was at T hot. There were two, one was T cold. T cold, They could both be hot. They could be very, very hot, but one is relative to the other colder. That's all that means. T cold doesn't necessarily mean it's frigid. It could be quite hot. So T hot and T cold are relative to one another, not in some absolute sense. Okay, so we see there that for ds, for this reversible operation of an engine, dq reversible over T surroundings, this is equivalent to saying that we have dq reversible over T system. Okay, so we can write it this way in terms of ds. Now, the important point here is that we proved a long time ago, and I won't prove it again here, but that dq irreversible, if you had a process going between two equilibrium states, one reversibly and one irreversibly, the heat interaction for the irreversible process would be less than that for the reversible process. And we proved this a long while ago. I won't go into it again. So if I divide both sides by T surroundings, in order to incorporate this relationship, or at least expand on it, I can divide both sides of this inequality right here by T surroundings. Okay. And I get this inequality. I divided by the same absolute temperature, so it doesn't matter. The equality still holds. There's no negatives here. Okay. But we know that on the right-hand side, based on the analysis and the discussion right here, that dq reversible over T surroundings is ds. Okay, that's what we just discussed right up above here. So I can write dq irreversible over T surroundings is less than ds. Okay. Is everyone okay with that? And so the important thing to remember here in this inequality is that I have irreversible right here. Okay. Now what I'm going to do is do away with any superscript on the Q. Okay, which means that that Q could represent a reversible or an irreversible process. And when I do that, I get dq over T surroundings. Now I have to incorporate the fact that if Q is irreversible, then the inequality holds. And if Q is reversible, dq is reversible, then the equality holds from here. So what I have is something like this, and on this side I have ds. Okay, because dq reversible over T surroundings is equal to ds. Okay, so these two can be made compactly, or can be reduced compactly into this inequality right here. Okay, this is, so now I have something that's related to this temperature of the external surroundings, the external to the system. Okay, and I remind you that this is sort of in line with what we had for P surroundings in this equation, right? That's the external pressure here. So I let that be P surroundings. So now I have something that's related to T surroundings right here. And that's good. I'm sort of building towards something that I can relate to with the surroundings. Perhaps I have a pressure stat or a thermostat, right? So maybe I want to connect to those things. And so let's see what happens. So I'm going to isolate the dq in this inequality just by multiplying by T surroundings on both sides. So what I have here is T surroundings times ds. Okay. All right. And so I have this expression for dq now in terms of temperature of the external environment relative to our system, and ds. And that's good because I can go back now to our fundamental relation, to building up our fundamental equation right here. And I know that dq is equal to du plus P surroundings times dV. So dq is equal to du plus P surroundings times dV. So what I'm going to do is substitute all of that for dq into this expression. So that's equal to du plus P surroundings times dV. And all of that, which is dq, is less than or equal to T surroundings times ds. Okay. And now I'm just going to put everything on one side and have 0 on the other. So I have du plus P surroundings times dV minus T surroundings times ds is less than or equal to 0. And this is an extremely important result as we discuss this part of this idea of spontaneity and stability. So any questions? Pardon me for sipping my coffee. Okay, good. So this is what we're going to now analyze in various cases. And so this is the fundamental equation, but now we've formulated it in terms of the pressure and the temperature of the surroundings, okay? Things that are external to the system of interest. And that's okay, because that's exactly how we run experiments. We have our system of interest, right? And it's not too difficult for us to envision that we can somehow control the pressure in the system. And even more easy to envision is the temperature. We can hook up a thermostat of whatever nature that thermostat may be to control the temperature. So that thermostat is external to the system. And so somehow, and that temperature is something we control, right? You control a knob. You say, all right, well, I want the temperature to be something. And nowadays, if you have something that's sophisticated, a nice sophisticated piece of equipment, you turn the knob or you push it, you know, whatever you do, and that's something that's external to the system. So now we have this relationship that is coupled directly to parameters of the external mechanism that we use to manipulate the system or to control the system. And that's really useful. That is extremely useful because it makes it practical now, right? Okay, so let's take a look at a few cases, okay? And these are going to be very cool and insightful cases. So the first case we ended up with last class, okay? Let's say we have an isolated system, okay? And we know that for an isolated system, dV is 0. Okay, like in the the Joule-free expansion, remember it was a rigid container. There's no volume change of the whole container. There's no change in the volume because it's rigid. And we also know that du is 0 for an isolated system. The energy of an isolated system is conserved. That's why it's isolated. Okay, I mean, it's self-consistent in that sense. So for an isolated system with these constraints then, right, what do we find? We find that minus, if we go back to our expression in this box that you see near the top of the screen, we have minus T surroundings times ds is less than or equal to 0 because the dV and the du terms are annihilated. We can multiply by minus T surroundings. And of course, this is absolute temperature. So T surroundings itself is positive. We multiply it by a negative, that thing becomes negative. And so now we're going to multiply by minus T, divide by minus T surroundings on both sides. And what that's going to give us is a change of sign here. And of course, when we multiply the other side by 0, it's just 0. Or divide by 1 over T, it's just 0. So what we find then, for an isolated system where volume and U don't change, we have this result here, okay, that for a system that's initially in an unstable state or a non-equilibrium state, what will happen is that entropy will increase, okay? So entropy S will increase in a spontaneous process in an isolated system, okay? If you have a spontaneous process. And then entropy S will not change, and this is something we know, will not change with time at in a stable equilibrium system. Okay, and so those conclusions are embodied in this inequality, ds greater than or equal to 0 for an isolated system. Okay, so this is very important. This is very important. And this is something we've already seen. And that's why I'm starting out with this. We've already seen this. It turns out then that U and V are the natural variables for S. Okay, and so we can write S and its natural variables, and of course N, S is extensive, it does depend on N, but for the purposes of this discussion, we can say that S has as its natural variables internal energy or energy U and volume. And this is very important because it's only when we control U and V that we can make this statement that entropy in a system increases for a spontaneous process. So we need to have some way to control U and V, i.e. we need to have a U stat, something that we can dial in a value of U, okay? And of course, that's not very practical. You've never heard in your careers so far, if you do experiments or you've read about experiments, any machine or mechanism that says, all right, I'm going to dial in U, right? And there's nothing that says, oh, on my knob, I'll set U to be 50, right? You can certainly do volume. You can manipulate the volume in some way, but U is a bit more nebulous. How would you do that? And it's actually not intuitive, nor is it direct. And so in this sense, using entropy to characterize processes may not be the most ideal or the most pragmatic, because the only way you can say that entropy in a system undergoing an irreversible or spontaneous process to evolve towards an equilibrium state, you would need to control U, right? Once you establish U, you can make this statement. Again, this is just reiterating the idea that this only applies for an isolated system. And in the universe, we know that the universe is one example of that, but it's really not that practical. Okay, so we can finally say that ds, which is now a function of its natural variables U and V, is greater than or equal to 0, and this is the way we would formulate it. ds, which is a function of its natural variables, internal energy U and V, is greater than or equal to 0 in a system that starts out in an unstable or non-equilibrium state and then is going to evolve. The evolution corresponds to ds increasing, ds greater than 0. And once that system reaches the equilibrium state or evolves to that equilibrium state, ds will be equal to 0. Okay, so any questions on that? Okay, and so that all stems from this equation that's at the top of the screen that's in the box, which is this fundamental equation which we manipulated to involve the external temperature and pressure, okay, so that we can couple that. All right, so let's go on to the next example. Okay, and we're going to get more and more practical now. Okay, but maybe not this one. This one may not be as practical. So let me write that equation again. Du plus P surroundings times dV minus T surroundings times ds is less than or equal to 0. And so again, it's all of this stuff which is less than or equal to 0. Okay. So this time what we're going to do, all right, is say that, all right, somehow I'm still going to allow volume not to change. So I'm going to say that I'm going to control volume in my system somehow, or for my system. So the system's volume is something I control. So dV is going to equal 0. Okay, so somehow, it's a rigid container, or I set the volume to whatever. So dV is 0. But now I have something like an entropy stat, i.e. by analogy to a thermostat or a pressure stat, I can make something called an entropy stat. Again, this doesn't exist, right? I'm just saying that if I could control the entropy, if I could dial it in, which we can't, but if we could, then in which case, then what would ds be? If I set it to a particular value, ds would just be then 0, because I've set it. I've set it to a value with my hypothetical entropy stat, just as I would set temperature, right? With temperature, with the thermostat, I would set T to be some value, because I want the system to be at a particular value, in which case then dt would be 0 because I set that temperature of the system. But in this case, I'm going to say I have an entropy stat, ds is equal to 0. So let's see what the implication of that is, going back to this expression, this very, very important expression. So if dv and ds are 0, okay, well, the second two terms cancel, and all we're left with is du is less than or equal to 0 in this system, if I were to be able to control volume and entropy, okay? If I could do that. So it seems then that U has its natural variables, S and volume, okay? So du seems to have as its natural variables, S and V. And for a system that's not initially in a stable state or is in a non-equilibrium state, the way du will evolve is given by this inequality right here. So what that means is the energy, once you have entropy and volume held at a particular value or not allowed to change, the energy of a system is minimized when volume and entropy are held fixed or they're controlled, okay? So many times in the past, perhaps you've been told that, oh, systems evolve or certain processes have been rationalized to you or for you by the statement that, oh, the energy is minimized. The energy is minimized. Well, now we see in this course, it's an upper level course, so we get a little bit more nuanced, that to say that the energy or something happens in a system that leads that system to evolve spontaneously or irreversibly, to say that it's this idea of energy minimization can only hold when the entropy of the system and the volume of the system are controlled to be at fixed values. Okay, that's the only, those are the only conditions under which you can say that the energy of the system is minimized in a process that happens spontaneously or reversibly. Okay, so this is U, energy or internal energy. Okay, that's how we're going to call this thing U. So there are very precise words that go with this idea of energy being minimized. If you're going to use the word energy or internal energy, it has to be with the words that entropy and volume of the system somehow are held at particular values or they're controlled by some mechanism. Okay. Okay. So now we just can't say, oh, well, the system evolves, a reaction occurs because the energy is minimized or something like that. Okay. Or the protein folds because energy is minimized or something like that, because that's not the total picture. It's only the total picture when you have S and V controlled or fixed. And this is given by this inequality and the idea that S and V now are the natural or inherent variables for U, because I've written it here. Okay, let's move on to now things that are going to be more practical. And now they're going to relate to things that are things you probably have heard. So any questions so far? So some very important concepts. So let me write the equation again, du plus P surroundings dV minus T surroundings ds. All of this is less than or equal to 0. Okay, so this time, what we're going to do is control temperature and volume. And so now we're getting into things that are more practical to control. So volume is good. We know that. We can appreciate that that's practical. Now we're going to get temperature to be controlled. So T surroundings is going to be used to control T system, which means T surroundings is equal to T system. We're going to control system temperature using the thermostat. Okay, so we're going to say that the T surroundings is equal to T system because of a thermostat. Okay, we're just going to let that be T. Okay, which means then that dt is going to equal 0 because we have temperature control through a thermostat. And we're going to have dV equal to 0 because we're going to control the volume in some way. Again, that I don't think that's too much of a stretch of the imagination for you to appreciate it. Okay, so dt and dV are 0 now. So what are the consequences of this? Okay. And we remember that T surroundings, which is the temperature of your thermostat, is equal to now the T system because we're coupling those two and we're allowing the system to have a constant temperature. Okay, that's something that we want to control. So let's see what this inequality leads us to. So dV is 0. So what I'm left with is du minus T ds when all of this is less than or equal to 0 in this system. Okay. Now I'm going to use the trick of derivatives, and the fact that dt is 0. Okay. So let me just sort of look at the total derivative of something that's the product of T and S. I can apply the chain rule. So if I want the total differential of TS, which is dTs, that's just T times ds plus S times dt. It's the first times the derivative of the second plus the second times the derivative of the first. In this case, they're the total differentials or the total derivatives. Okay. We just keep in mind when we write this that dt is 0 for our case because we're controlling temperature through this thermostat. Okay, but it's okay. And so since dt is 0, dTs is just going to equal TDS. Okay, because dt is 0 by construction, so that dTs is equal to TDS. But look at this, we have TDS right here. Right? We have a TDS term right there. So what that sort of seems to suggest, if we allow TDS to equal dTs in this case because of constant temperature, we have du minus dTs, and all of that is less than or equal to 0. Okay, so I have the the total differential of u minus the total differential of Ts. That whole thing is less than or equal to 0. But what I'm going to do is just put the u and the Ts together. I can do that because they're both in that d something. Okay. So what I can write this as d of u minus Ts, and that whole thing is less than or equal to 0. And if you want me to see this thing in blue, this last expression here would just be du minus dTs, okay? But we know that that's du minus TDS minus SDT. dt is 0 in this case, so this term goes away. And what we're left with, if you just want to convince yourself, is this guy right here, du minus TDS, okay? But in this case, we see that we have the total derivative of something that's u minus Ts. U is a state function, T is a state function, and S is a state function. So this total derivative here of u minus Ts represents the total derivative of some state function. And that state function now is something that you've heard about. It's called the Helmholtz free energy. And we're going to label it A. A is defined as u minus Ts. And this is the Helmholtz, And it comes out nicely from our analysis of this inequality for spontaneous and irreversible processes. So this leads to A, and we see that A now is dependent on a few parameters, and we'll see that in a moment. dA is less than or equal to 0. Okay, that's coupling to that expression right there. So this thing called A, which is the Helmholtz free energy, is minimized in an irreversible or spontaneous process of a system under conditions where the temperature and volume are controlled precisely. And precisely is, again, this rather arbitrary word I'm using here, but we'll just take it that you can precisely control the temperature to some degree, okay, acknowledging that there's some uncertainty in that. So we see here again that A, this thing called Helmholtz free energy, is minimized in a spontaneous or irreversible process in a system which is held at constant temperature and volume. So all of those words have to be said together for this thing to make any sense. Okay. And so what are the natural variables for A? Well, let's just use this expression to figure this out. Okay. And that's going to make some sense. So we know that A is equal to, defined as U minus TS. Okay. So we can take the total derivative of A, or the total differential. So dA is going to be du minus dTs. Okay. And this now in the most general form, du we know is TdS minus PdV. Okay, this is the combination of our first and second laws, the fundamental equation. So du is equal to TdS minus PdV. And this minus dTs term is going to give us minus SDT minus TdS. Okay. And so what happens is that this TdS is going to cancel with that TdS. And what we have here is dA is equal to minus PdV minus SDT. Okay, and that's very important because that tells us that A, the Helmholtz free energy, is a function of what? Temperature and volume. But wait a second. Temperature and volume were the two things that we controlled in this experiment. So it's nice that A turns out to have as its natural variables temperature and volume. And in fact, it's not nice. It had to be that way. It's not surprising, but it's just very cool that that's how it happens. Okay. So this thing called Helmholtz free energy, which is minimized when you hold temperature and volume of a system constant during an irreversible or spontaneous process, has as its natural variables temperature and volume. So now we can write this criterion for spontaneity of a process in a system under conditions of constant temperature and volume as dA, which is a function of temperature and volume, is less than or equal to 0. So the inequality less than 0 holds when you have a spontaneous process through which the system evolves from a non-equilibrium state to an equilibrium state irreversibly, and the equality holds once that system reaches equilibrium and is stable. Okay, so dA is equal to 0 at stable conditions of equilibrium. A is a function of temperature and volume, and I reiterate then that the total derivative of A, this Helmholtz free energy, is this guy. That's very important. We see here very explicitly that A is a function of temperature and volume when we look at its total differential. So any questions on that? This is very important. Any questions at all? All right. So that's good. So it tells us then, if we can control the temperature and volume of a system, which we can, these are very practical things. These are practical knobs. So this is good. So that means this Helmholtz free energy is quite useful. This is now getting to be very, very useful because we can say, right, that for an irreversible or spontaneous process in a system, the Helmholtz free energy is minimized when you can control the temperature and volume of the system precisely, or to within the precision of an instrument, or to what the system will allow you to do. Okay, now we're getting to something very, very useful, but we have to keep in mind the conditions of the experiment. Okay, that's very important. You can't just neglect that, right? Because that's important. And if someone wants to repeat or reproduce your experiments, you have to be that precise in letting them know. But if conditions of temperature and volume are controlled, then you know that you have to talk about the Helmholtz free energy when you're talking about processes in a system. That is the governing fundamental thermodynamic potential that is relevant to a system in which temperature and volume are controlled and fixed. dV is 0, dt is 0. Now let's look at I think this is probably the most practical. When temperature and pressure are controlled, right? Those are the two things that we control most often directly, temperature and pressure. So let me write our expression again, du plus P surroundings dV minus T surroundings ds. And all of this is less than or equal to 0 that we found earlier on. And so now what we're going to say is dt is 0 because we're going to use a thermostat so that T surroundings is equal to T system, and that's equal to T. Okay, we're going to have a thermostat. And we're going to say that dP is 0 in the system because P surroundings is equal to P system is equal to P. We're going to control the pressure. Okay, just as we did early on with those piston cylinder assemblies with some external mechanism. You could have any mechanism you want to control the pressure. So dt and dP are 0 in this case. Okay. So let's see what sort of consequences arise from this expression here. All right. Let's see here. Let's see, we can do the same thing we did before. We have these terms here in our expression here for the inequality, a PDV term and a TDS term, because P surroundings is equal to P system, which is equal to P, and T surroundings is equal to T system, which is equal to T. So that's just a PDV and a TDS kind of like term. But we saw above that DTS is equal to, sorry, D of the product is TDS minus SDT. Okay, and in this case, since we're controlling the temperature, we said dt is 0. So dTs is going to equal TDS, only in this particular case, because dt is equal to 0. Okay, we can write the same thing for PV. D of PV is equal to PdV plus VdP. But we said that dP is 0 because we're controlling the pressure. And so the second term is going to cancel and we're going to be left with D of product PV is just PdV. Did I make a mistake or am I okay with that? Yeah, that's good, right? Very good. Okay, so what we can do now, since dPV is equal to PdV, we have a PdV term up here. We have PdV. So I'm going to let that PdV equal D of PV, and the same thing for that TDS term. And what that gives us is this. Okay, so I'm going to take this and rewrite it, okay, using this and this. So these two I'm going to use. So du plus, so the PDV term is just a D of PV, and that minus T surroundings ds or TDS term is just minus dTs, and all of this is less than or equal to 0. Okay, but what I have is the total D of U, the total D of PV, the product PV, and the total D of the product TS. I'm going to combine those total differentials in this way. D of U plus PV minus TS. I can do that, and that's going to be less than or equal to 0. Okay. Any questions on what I just did there? Okay, good. That's really good. And now, whatever is in this in the parentheses, those are all state functions. U is a state function. P and V are state functions. T and S are state functions. So we have now created a new state function, or something has popped out when we've let pressure and temperature be held constant. And that new thing, okay, is called G, which is U plus PV minus TS. But we know from earlier on that U plus PV is this thermodynamic potential called H. Remember, that was enthalpy. So G is defined as H, which is U plus PV minus TS. And this, I think can everyone yell it out? Does anyone want to yell it out? You know what function that is?
Gibbs free energy.
That's the Gibbs, that's the famous Gibbs free energy. So this is the famous Gibbs free energy, which pops out of our analysis when pressure and temperature are held constant or they're fixed by some external machines or mechanisms. And that's the most practical, right? And so this is why this Gibbs free energy is so central to everything in science and engineering. It's at the heart of everything. And so we're going to focus a lot on G for the rest of the course because it's so important. So G is H minus TS, okay? So what that means is that dG, if we go back to this inequality here, right here, dG is less than or equal to 0 for our case purposes when T and pressure are held constant. Now we just need to know what the inherent variables are for G, and then our story will be complete. So let's take a look at that. G is defined this way or this way. We'll use that first expression. So dG is equal to du plus pdv plus vdp minus tds minus sdt. And all I've done here is expand those dpv terms. So the total differential of a product, again, using the chain rule, allows you to expand it. And I know what du is. Du is tds minus pdv, which is this guy. And then I add everything else in, pdv plus vdp minus tds minus sdt. Okay, so this TDS is going to cancel with that. This minus PDV is going to cancel with that PDV. And what I'm left with is DG is equal to this term, VDP, and this term minus SDT. And so we see here, when we have no change in moles yet, G is a function of pressure and temperature. Wow. Those are exactly the two variables that we controlled in the system, right? So it turns out that this thermodynamic potential G is inherently a function of pressure and temperature, and that's the thing that is going to be used to govern or formulate whether a system evolves from one state to another irreversibly, i.e. spontaneously, or not. And so what we have then, dG of temperature pressure is less than or equal to 0 is our guiding principle for spontaneous processes and systems that are held at constant temperature and pressure. So if you have a system in which you control the temperature and pressure, initially that system is not in an equilibrium state, it's in an unstable state. What will happen is that the system will reduce, i.e. minimize its Gibbs free energy until it reaches an equilibrium state. And in that equilibrium state, G will no longer change and dG will be 0. Hence, you have a stable state, an equilibrium state. And that's embodied to this inequality here. Okay? And since we know now that G is defined as H minus TS, okay, dG is equal to dH minus d of TS. Okay. And so if we have a system under constant temperature, right, we can have dG is equal to dH minus TDS minus SDT. I think it's, yes, H minus TS, right? And if temperature is constant, this term goes to 0. And what we have is dG is equal to dH minus TDS at constant temperature. Of course, constant pressure too, okay? But if temperature is constant, dG is equal to this. And we know that this is less than or equal to 0 based on our analysis here. So what that's saying is that this DH minus TDS is less than or equal to 0. Okay, at constant temperature and at P is equal to constant. Very important. So this is an extremely profound result, and you've heard of this before. This thing G, which is now minimized in a spontaneous process under conditions of constant temperature and pressure, is composed of changes in H, which is enthalpy, and changes in S, ds, which is entropy. And what you see here, because G is minimized in a spontaneous process, it's this combination of H, entropy, and enthalpy and entropy, the combination of their variations, which leads to the total change in G, which is now being minimized in a spontaneous or reversible process. This is what is known as enthalpy-entropy competition, or the pulling and pushing, or whatever it is, the push-pull of entropy and enthalpy in a system. This is exactly how it arises. Okay, so Gibbs free energy is minimized in a spontaneous process in a system under conditions of constant temperature and pressure. All of that has to be said for any of it to make sense or to have meaning. Okay, and this thing is loaded because now we see that because temperature and pressure are very practical things to control, that Gibbs has to be, or it's a good thing that something like Gibbs arises for us to speak about, because it is central when you have conditions of constant temperature and pressure. The natural variables of Gibbs are temperature and pressure. And when you control temperature and pressure, you talk about Gibbs and what it does in spontaneous and irreversible processes. Furthermore, if we dig a little bit, knowing what G is, it's this combination of enthalpy and entropy, we see that since G is minimized, it's this combination of enthalpy and entropy as they push and pull, because enthalpy, DH is plus, in this case, ds is associated with a minus. They have to go in opposite directions in order to minimize G. H has to be going negative, or it has to be getting smaller in order for G to get smaller. But since ds is associated with a negative sign and we use absolute temperature, entropy has to increase. Okay? So we have entropy increase or enthalpy decrease leading to this change in G. What this means is that in a system at constant temperature and pressure, entropy actually can decrease. Entropy can decrease as long as the enthalpy compensates for that decrease in entropy, such that the overall combination, this overall addition of enthalpy and entropy, leads to dG being less than 0. And that is really an important point to take away from this, is that since G is this combination of enthalpy and entropy, each with a different sign, okay, entropy actually, under conditions of constant temperature and pressure in the system, can decrease as long as the enthalpy compensates for that decrease in entropy by being negative, by being more negative. Okay, so this is a very important result. Okay, and it's something that we will now pursue for the remainder of the course. So Gibbs free energy. Any questions? I hope that was clear, and why G is now the focal point. And we're going to now massage and manipulate G to get at results that you've seen before in some of your courses without any proof or any demonstration of how they came about because of G. Okay, great. Thank you for your attention and contributions. Any questions before I end? Or comments? Okay, awesome. Have a great week. And here's a little saying: if you want to be a super spreader of contagion, then smile often and smile a lot, and you'll spread a contagion. Okay, thanks everyone for your attention. And I guess I'll be here for office hours if you have any questions. Okay, be well, be safe.